Good morning all. Today we are discussing the last portions of amplitude modulation. We discussing the power in amplitude modulated wave. We know that the power can be written as I square into R or V into I or V square divided by R. Here we use the expression of power that is V square divided by R. We know that the power dissipated in circuit is a function of square of the voltage across the circuit and the effective resistance of the circuit. Then power can be written as power is equal to V square divided by R. Here in the case of amplitude modulated wave, it is a sinusoidally varying wave. So the voltage must be considered as the RMS value. So we write the expression of carrier power as PC, that is equal to EC divided by root 2 whole square divided by R. Here the root 2 come from the conversion to RMS voltage. Then it is equal to EC square divided by 2R. It is the carrier power. Carrier power PC is equal to EC square divided by 2R. And we know that in an amplitude modulated wave, there are two sidebands. Then the total power of sideband must be the sum of powers of the two sides. Then we know that the amplitude of the sideband, it is equal to MEC divided by 2. Then root 2 comes from the conversion to RMS value. Then MEC divided by 2 root 2 whole square divided by R plus it is for the next sideband. It is for the lower sideband MEC divided by 2 root 2 whole square divided by R. Then it becomes M square EC square divided by 8R plus M square EC square divided by 8R. Then a total gives M square EC square divided by 4R. Then the total power of AM wave must be is equal to sum of carrier power and the total of the sideband power, that is PC plus PS. The total power can be sum of these two values, AC square divided by 2R plus M square EC square divided by 4R. Then here an EC square divided by 2R is taken outside. Then in brackets it is 1 plus M square divided by 2. Then we cross multiply the quantities in brackets. Then we write EC square divided by 2R into 2 plus M square divided by 2. 2 plus M square divided by 2. Then it can be obtained the fraction of total power carried by sideband. The fraction of total power carried by sideband. That is a ratio of sideband, total sideband power to the total power, that we have to find the ratio of equations of 2 and 3. That is, this quantity is equal to M square AC square divided by 4R, and here PT is equal to EC square divided by 2R into 2 plus M square divided by 2. Then it becomes M square divided by 2 plus M square. It is the fraction of total power carried by sideband. As the signal is contained in the sideband frequency, therefore, the useful power is in the sidebands. Then looking at the expression, we can infer that the fraction of total power carried by sideband depends upon the modulation factor M. That is PS divided by PT is equal to M square divided by 2 plus M square. Then it depends on the modulation factor. If the value of M is greater, then the useful power carried by sideband must be greater. That is, if PS by PT is greater, that means useful power carried by sideband must be greater. Then for greater M value, the useful power must be high. When M is equal to 0, the power carried by sideband must be equal to 0. That is, here 0 square divided by 2 plus 0 square, it gives 0. And when M is equal to 0.5, the power carried by sideband can be obtained as 11.1% of the total power. And when M is equal to 1, the power carried by sideband is 33.3%. Then the limitation of amplitude modulation. Although the amplitude modulation construction is very simple, it has some limitations of noise. Then the first limitation is the noisy reception of AM wave. And the second is low efficiency. And the third is small operating range. And fourth is the lack of audio quality. These are the limitations of amplitude modulation. Then we go to the next session, that is frequency modulation. We know that in the frequency modulation, the frequency of the carrier wave is changed in accordance with the intensity of the signal. That is, the frequency of the carrier wave is changed in accordance with the intensity of the signal. It is called as frequency modulation. In frequency modulation, only the frequency of the carrier wave is changed in accordance with the signal. In frequency modulation, the amplitude of the carrier remains a constant, but the frequency changes. In the amplitude modulation, only the amplitude of the carrier changes, frequency constant. Here the frequency of the carrier is changed and the amplitude remains constant. Then frequency modulation, frequency of the carrier wave is changed in accordance with the signal. Look at the figure. In top, the modulating signal is given and the carrier wave with high frequency is given, and in the bottom it is a frequency modulated wave. That is, the carrier wave frequency is changed in accordance with the intensity of the signal. We consider the different points marked in the signal. Then looking at the signal, in the points A, C, E and G, the amplitude of the signal is 0. If the amplitude is 0, then there is no variation in the carrier frequency. Then the carrier frequency unchanged. Okay. And at the points B and F, here at the point B and F, the amplitude is maximum. Then maximum change occurred at the frequency. That means the frequency increased to a maximum at the points B and F. Okay. And then the point D. Point D is the minimum amplitude. Then the carrier frequency is reduced to a minimum as shown in figure. For minimum frequency, it is the wave is widely spaced, and for maximum frequency, it is closely spaced. The frequency deviation of FM signal depends on the amplitude of the modulating signal. The frequency without modulation, or when the modulating voltage is zero, is called center frequency. And the audio frequency does not determine the frequency deviation. The first point say that the frequency deviation depends on amplitude of the modulating signal. Frequency deviation means the variation in frequency of the carrier. Here, looking at the figure, a frequency modulated wave is shown and the frequency at the different parts is given. Here, at 3 points, a frequency of 100 Hz is given, and in some points, here a 133 kilohertz and here a 70 kilohertz is shown. Then 70 kilohertz is the lowest and 130 kilohertz is the largest. Then here the 100 kilohertz must be the center frequency, and the deviation from the center frequency to the upper side and lower side, that must be 30 kilohertz. That is the difference between 100 kilohertz and 70 kilohertz must be 30 kilohertz, and similarly the 130 kilohertz and the 100 kilohertz, its difference must be 30 kilohertz. Then the FM deviation, frequency deviation is 30 kilohertz. Then the advantage of frequency modulations. Here, the sum of the limitations by the amplitude modulation is overcome by frequency modulation. That is, it gives noiseless reception. And the second is the operating range is quite large. It gives high fidelity reception, and the efficiency of the transmission is very high. And then we go to the theory of frequency modulation. In the frequency modulation, the amplitude of the carrier is kept constant, but the frequency of the carrier is varied by the modulating signal. That is, here we consider the frequency of the carrier wave as Fc. Then that Fc is changed or varied according to the intensity of the modulating signal. The carrier frequency Fc varies at the rate of signal frequency Fs, the frequency deviation being proportional to the instantaneous amplitude of the modulating signal. The maximum frequency deviation, that is Fc max minus Fc, that occurs at the peak voltage of the modulating signal, and the minimum suppose a modulating sine wave signal Es is equal to Es cos omega st is used to vary the carrier frequency Fc. That is, the signal is represented by Es, where small es used to express the instantaneous sine wave signal. Let the change in carrier frequency be k into Es, where k is a constant that is known as the frequency deviation constant. That quantity will define in the upcoming session. Here we take the change in carrier frequency be k into Es, where k is the constant known as frequency deviation constant. The instantaneous carrier frequency can be written as Fc plus KES. Here in frequency modulation, the frequency changes and Fc is the center frequency or the frequency of the carrier, and KES is the change in carrier frequency. Then the instantaneous carrier frequency Fi is given by Fi is equal to Fc plus KES. Then it is equal to Fc plus K into Es cos omega St. Then look at figure. The figure shows the instantaneous carrier frequency versus time. It is important to note that it is a frequency time curve and it is not an amplitude type. It is a frequency time curve and it is not the amplitude time curve. That is, in the x-axis, we mark the frequency of the signal, carrier signal, and in the x-axis, the corresponding time. Then the frequency is increases and become a maximum value, then it reduces to a minimum value, then this cycle goes on. The factor k into Es represents the maximum frequency deviation and is denoted by delta F. Here the factor KES. Here it is Fc and the difference here must be KES, and up to this it must be KES, and the factor KES is the maximum frequency deviation and is denoted by delta F. then the maximum frequency deviation delta f must be equal to k into Es. Then using this definition, that is delta f is equal to KES, we rewrite the expression of Fi as Fc plus delta f into cos omega st. Then the equation of Fm wave. From the above expression, that is Fi is equal to Fc plus delta Fc cos omega st, we write the instantaneous angular frequency as omega I is equal to omega c plus delta omega c cos omega st. Okay. Then the total phase change, angular change, can be written as theta, that is equal to omega into t. Okay. Then we can written as theta must be equal to integral 0 to t omega I dt. Then we substituting the value of omega I here. We can express theta is equal to integral 0 to t omega c omega delta omega c cos omega st dt. Then integrating these two terms separately, we will obtain theta is equal to omega ct plus delta omega c sin omega st divided by omega s. That omega s is given here. Then delta omega c divided by omega s into sin omega t. We define this quantity delta omega c divided by omega s is called as modulation index MF. Modulation index MF. It is not the modulation factor. Here we define delta omega c by omega s is the modulation index. Then the expression is written as theta is equal to omega ct plus mf sin omega st. The instantaneous, here we obtain the value of theta, angular part. Then the instantaneous value of Fm voltage can be written as it is equal to Ec cos theta. Why we write this way? Because in Fm modulation, only change occur at its frequency part. Then it is the theta is corresponding for omega t. Then omega changes. Then for theta, substitute this quantity, then it is equal to Ec is equal to cos omega cos of omega ct plus mf sin omega st. From this expression we can infer that the frequency of the carrier is changed according to the signal. Here's some point to be noted that the modulation index MF is the ratio of maximum frequency deviation to the frequency of the modulating signal. Delta F divided by delta f divided by fs. Okay, it is the modulation index. In amplitude modulation, we restrict the value of modulation factor in between 0 and 1. But here, the modulation index MF can be greater than unity. Modulation factor in the case of AM cannot be greater than unity for a good modulation, but here it can possible. MF can be greater than 1. Next is the frequency spectrum of frequency modulation. If Fc and Fs are the carrier and signal frequency respectively, the FM spectrum will consist of the following frequencies. That is, it will consist Fc and Fc plus or minus Fs, Fc plus or minus 2Fs, Fc plus or minus 3Fs, and so on. If we draw a spectrum, then it will occur a central frequency Fc, and in the both side a number of frequencies in upper sideband and lower sideband. Fc plus Fs and Fc plus 2Fs, Fc plus 3Fs are at the upper sideband, and Fc minus Fs, Fc minus 2Fs, Fc minus 3Fs, etc. are at the lower sidebands. Then the comparison of frequency modulation and amplitude modulation. Mainly there are 4 differences. That is, in frequency modulation, the amplitude of the carrier remains the constant with the modulation. But in AM, the amplitude of the carrier changes with the modulation. And in the frequency modulation, the carrier frequency changes with modulation. In AM modulation, the carrier frequency remains constant with modulation. And in FM, the carrier frequency changes according to the strength of modulating signal, and in AM modulation, the carrier amplitude changes according to the strength of modulating signal. And in FM, the value of modulation index MF can be more than 1. In AM, the value of modulation factor small m cannot be more than 1 for distortionless AM signal. This is the details of frequency modulation and amplitude modulation. Mainly, we have to discuss the 2 types of modulation in detail, and next we have to discuss the demodulation process and the pulse modulation process in brief. Okay, thank you.